Telescopes are an astronomer's most powerful tool for looking back in time. Now, traveling back in time is the stuff of science fiction, but looking back in time is science fact. It's something that we actually do, and it's made possible by the finite speed of light. And so, if one looks at, say, a person in the room next to you, you aren't seeing them as they are right now. You're seeing them as they were a few nanoseconds ago. That's how long it takes light to travel about a meter. When we look at the sun, we're not seeing it as it is. We're seeing it as it was 500 seconds ago. If we look at the nearest star, Proxima Centauri, we see it as it was 4 years ago. With the James Webb Space Telescope, we are looking back in time more than 13 billion years to see the birth of the first stars and galaxies to form after the Big Bang. But to do this, we face a fundamental challenge. The light from the first stars and galaxies was emitted in the ultraviolet and visible parts of the spectrum. But as that light travels to us through expanding space, its wavelength is stretched to infrared wavelengths. And so, to observe it today, we have to work in the infrared. For decades, this made seeing the universe's first dawn an impossible dream, because we simply didn't have the tools. How, then, do we see the light from the universe's first chapter? The answer lies in a new kind of observatory, with capabilities we've never had before. To understand how Webb accomplishes this, we first need to grasp the problem it was built to solve. When we look out at the cosmos, every telescope is a time machine. The Andromeda galaxy, for instance, is about 2.5 million light-years away. The light we see from it tonight began its journey when early human ancestors were first walking the Earth. The farther we can look, the deeper into the past we see. This presents us with a remarkable opportunity. If we could build a telescope powerful enough to see an object 13.5 billion light-years away, we would be seeing light from the universe when it was just a toddler, a tiny fraction of its current age. We could witness the formation of the very first galaxies. But here is the challenge. The universe has been expanding ever since the Big Bang. It isn't that galaxies are flying apart from each other through space, but that space itself is expanding, carrying the galaxies with it. Think of a wave drawn on a rubber band. As you stretch the rubber, the wave itself stretches out, its peaks growing farther apart. The same thing happens to light. Light from the earliest galaxies started its journey as high-energy visible or ultraviolet light. But over 13 billion years, as space has expanded, that light has been stretched. Its wavelength has been elongated so dramatically that by the time it reaches us, it has been shifted past the red end of the spectrum and deep into the invisible realm of infrared light. This is called cosmological redshift. For all its power, the Hubble Space Telescope is primarily an optical and ultraviolet instrument. It could get a fleeting glimpse into this ancient red-shifted universe, like with the galaxy GNZ11, but it wasn't designed for this work. The most ancient light in the universe was written in an ink it couldn't fully read. This is where the James Webb Space Telescope comes in. The telescope looks, frankly, different than most other telescopes that you've seen pictures of. And all of those differences you see are there to enable Webb's unique science mission, to see the birth of the first stars and galaxies, and to give humanity its first high-definition view of the infrared universe. So, the things that make JWST unique are its infrared capability in combination with the very large size of its primary mirror. To see the most ancient objects, you simply must look in infrared light. There's no other way, because the universe's expansion has transformed that light. But there's a second, equally important reason. The early universe was a dusty place. Stars and planets form inside vast, dense clouds of gas and dust. These stellar nurseries are opaque, and visible light can't get through. Infrared light, however, has a longer wavelength that allows it to penetrate this dust. By observing in infrared, Webb can peer directly into the hearts of these clouds, to witness stars and planetary systems in the very act of being born. Webb's infrared vision, therefore, does two things. It acts as our time machine to see the red-shifted light from the first galaxies, and it allows us to see through the cosmic dust that obscures star formation. Building a machine to do this is one of the most difficult engineering challenges ever attempted. It requires a telescope that is incredibly large, exceptionally cold, and positioned perfectly in space. To see the faintest, most distant light, you need a very large mirror to collect it. The giant primary mirror that JWST has is the first time that any infrared telescope in space has had a mirror of this size. At 6.5 meters across, it was too large to fit in a rocket, so it was designed to unfold in space like origami. The mirror is made of 18 hexagonal segments of beryllium, a metal that is both light and very strong at cold temperatures. Each segment is coated with an exquisitely thin layer of gold, which is exceptionally reflective of infrared light, maximizing the telescope's ability to capture every precious photon. But for an infrared telescope to work well, it has to be made very, very cold. Anything that is warm emits infrared light. If we didn't make the telescope very cold, it would be blinded by its own infrared emission. And so, JWST does not orbit the Earth the way the Hubble Space Telescope does. It was sent to a special spot in space called the second Lagrange point, or L2 for short, 1 million miles from Earth. We determined that if we put JWST at this special spot, all the major sources of heat, the Sun, the Earth, and the Moon, would always lie in the same direction. So we realized we could deploy a giant sunshield, the size of a tennis court, so that the telescope will always live in its shadow. In that configuration, it cools passively, by simply radiating its heat away to the cold darkness of space. The cold side, where the mirrors and instruments are, reaches about -233 degrees Celsius. One instrument, the mid-infrared instrument, or MIRI, needs to be even colder, so it has its own cryo-cooler that chills it to just 7 degrees above absolute zero. This combination of a giant golden mirror, a massive sunshield, a stable orbit, and cryogenically cooled instruments is what gives Webb its power. The images it produces are as breathtaking as the Hubble images. And this is the first time that humanity has seen the infrared universe in high definition. So, with this incredible observatory in place, has it found what it was looking for? The answer is an emphatic yes, and the discoveries are more spectacular than we predicted. Before Webb, the most distant confirmed galaxy was GNZ 11, which Hubble saw at a time about 400 million years after the Big Bang. Within its first year of science operations, Webb shattered that record. Recently, through the JADES program, astronomers confirmed the galaxy JADES GSZ 14-0, which we are seeing as it existed just 290 million years after the Big Bang. This is an era of the universe we had never observed before, when it was only 2% of its current age. What's surprising is what these galaxies look like. Our models predicted that the first galaxies would be small and somewhat disorganized. But JADES GSZ 14-0 is surprisingly large and incredibly bright. Finding a galaxy this luminous and developed so early challenges our theories about how quickly the first structures could have formed. Webb is also uncovering the secrets of the first supermassive black holes, finding that they grew very large, very quickly. And its spectrographs are doing cosmic chemistry, analyzing the light to find the signatures of elements like carbon and oxygen. Finding them this early tells us that several generations of stars must have already lived and died within the universe's first few 100 million years. Webb has transformed our view of the early cosmos from a few faint smudges into a rich landscape of unexpectedly complex galaxies. The James Webb Space Telescope has given us the ability to see the invisible, ancient light from the beginning of our universe. We set out to find the cosmic dawn, and we found it. But in doing so, we've uncovered deeper questions. How did galaxies and their black holes grow so big, so fast? What were the first stars like? Our whole lives are just a fleeting moment. The day-to-day tribulations that we torture ourselves with here on Earth, all of it is terribly insignificant in terms of this universe that we're embedded in and that is evolving around us. The big picture is not the picture we spend most of our time arguing about, and I'm hopeful that we'll be able to avoid destroying the Earth long enough for us to really understand the universe we're embedded in. Webb's journey is far from over. It will continue that process, doing spectroscopy to understand the chemistry of exoplanet atmospheres. We now know that worlds exist around nearly every star in the galaxy. There are billions of habitable worlds in our galaxy alone, and there are billions of galaxies. The search for extraterrestrial life is no longer the stuff of science fiction. It's somewhat inconceivable that we are alone. Now, we need to begin the long, methodical business of searching for life, and this will be some of the most exciting science we do over the next few decades. The detective is still on the case, and the greatest discoveries may yet lie ahead.